All right, guys. So let's go ahead and get started with completing the reference test review sheet that I gave you guys during class. Okay. So let's go through these problems one by one and figure out what's the correct responses will be. I know some of you guys did this in class today, which is perfect, but here's another opportunity for you guys to hear it again. Okay. So for the first problem, number 7, it's asking for the following reactions. We're going to state whether the reaction is going to occur or will not occur. Okay. So perfect, easy, yes or no answer. Okay. So if it is a yes, though, if it's a if the reaction can occur, then we have to complete the reaction. Okay. Not too hard though. Okay. It's not too hard because remember we've learned this already once before. All right. Pardon me, my allergies. So first one we have is iron plus tin bromide. Can this reaction occur? So remember, this is a single replacement reaction because we have a single element trying to replace with the tin right here. Okay, so what we have to do here is we have to go to our reference sheet, which is this guy right here, and we have to look for tin and I forgot what the other one was. We have to look for tin and iron. So iron has to be stronger than tin in order for that reaction to occur. Okay, so let's look at, whoa, what was that? Let's go ahead and take a look at the activity series, because remember the activity series of metals is what's going to help us determine if the reaction can occur or not. Okay, so we're looking at iron and tin. So here we have iron right around here, and right here we have tin. So iron, we could tell, is higher on the activity series compared to tin. So that will mean that iron has the strength to replace tin in this compound right here. Okay, so our answer here would be yes. And then iron will replace will replace tin to knock tin by itself right here. And then we're gonna have iron bromide. All right. So that will be your two reactants. Okay, tin plus iron bromide, because the iron kicked out tin from the compound and made a new compound. Okay, so let's look at potassium chloride and iodine. So iodine here is by itself, and it is a non-metal. So if it's a non-metal, it wants to replace the other non-metal. Okay, so that means we have to look for iodine and chlorine. So we have to see if iodine is stronger than chlorine in order for the reaction to occur. So we go back to our reference sheet. We go to the non-metals. See here, non-metals. Is iodine stronger than chlorine? Does not look like it. Okay, so then we come back over here. And since iodine is not stronger than chlorine, we write no. Okay, so for the test, just make sure you're able to read the activity series and be able to decide whether an element is strong enough to replace another element in a single replacement reaction. All right. So calcium is trying to replace another element here in magnesium fluoride. So is calcium a metal or non-metal? Correct. It is a metal. All right. So if calcium is a metal, it's going to want to replace the other metal in this compound, which is magnesium. So again, we look at our activity series. We look up calcium and we look up magnesium. Okay. Is calcium stronger than magnesium? Calcium is indeed stronger than magnesium. Okay, so we go back to our response here, and then we are going to say, yes, it is stronger. Okay, so calcium kicks out magnesium and makes magnesium hang out by himself. Okay, and then it's going to be bonded now. Calcium is going to be bonded with sulfur, which to make it still sulfide. All right. If you guys have any questions, guys, please don't be afraid to email me. and we should be good to go. Okay. All right, and last but not least, for part D, we're going to look at bromine. Since bromine is a nonmetal, we want to see if bromine is capable of replacing the nonmetal here, which is fluorine. Okay, so we look at bromine. Is bromine stronger than fluorine? Bromine's right here, and it is indeed not stronger than fluorine. So we come back over here, and we go ahead and write a big no, that it is not stronger. So there's no reaction. Okay, so there's no reaction here. And no reaction here, all right? So the diatomic molecules. So remember, diatomic molecules, we're transitioning into diatomic molecules or elements, okay? So remember, these elements have a natural bond with itself in order to be stable in a reaction, okay? So for example, whenever we list hydrogen, we don't write just an H. We have to write an H with the subscript of 2, because this is the way it occurs naturally in society or in our world, okay? So remember that nice acronym that I think it's an acronym, oh well. Hofbrinkel. All right. Oh, nah, that's a lowercase l. See, Mr. Delgado's already messing up. Let's go back to my pen, and it is a lowercase l. So Hofbrinkel. Don't forget this. Okay, these are our 7 diatomic molecules. We have hydrogen, oxygen, fluorine. We have bromine. We have iodine. Well, can't forget that too. We have nitrogen. And then last but not least, we have chlorine. Okay, so these occur naturally bonded to itself. All right, moving on. Number 9. So number 9, we're calculating the molar mass. So in order for us to do the molar mass, remember, we list the amount of atoms that are a part of the compound. So here we have 1 Na, we have 1 Br. Okay, and we're going to multiply it by its molar mass. And if we look at our periodic table, for you guys will be using your reference sheet. If we look at our periodic table, we look for Na, and it's right here. Whoa, why did you do that? Why is it doing that? Oh. So here I have Na, and it has a molar atomic mass of 22.99, which, since it's 0.99, we could round up to a nice even 23 grams per mole, okay? And then bromine, if we look up bromine in our periodic table, we see that bromine has a mass of 79.9. Since it's 0.9, okay, 79.9. If it's only a 9, it's not 99, we want to keep it, okay, because we want to be as accurate as we can. Okay, so it is going to be 79.9 grams per mole, okay? Over here, H2S, here I have how many H's? I have 2 H's. How many S's do I have? I have 1 S. Figure out, look at my periodic table, I see I have 1.01 grams per mole of hydrogen. What's my atomic mass for sulfur? I see that sulfur has a mass of 32.07 grams per mole. And then last but not least, we multiply, and then here we get 2.02 grams per mole. Here I still have 32.07 grams per mole. And then last but not least, we got to add them together, and then we get 34.3. Whoa, 0.3. Lies. Pen. 34.0 0.9 grams per 1 mole. Remember, this is another way we could write it, correct? And then if we were to do these, remember we just sum these together because there's only one, we would get 102.9 grams per mole. All right. And then grams per mole of what? NaBr. And then for this one would be H2S. So I'm going to leave this one for you guys to do on your own, okay? You guys should have done this in class already as well, all right? So let's keep it rolling. Number 10, a blank is used to measure the number of representative particles. It's what we've been working on for the past 2 weeks. It is the mole. A mole is used to measure the number of representative particles. And this number is equal to 6.02 times 10 to the 23. And this number is also referred as to the Avogadro's number, all right? Number 11, how many grams does 1 mole of carbon weigh? So 1 mole of carbon. So I was just saying 1 carbon atom. That's all it's asking. How much does this 1 carbon atom weigh? So we look it up on our periodic table and we see that it is 12.01 grams. And then how many grams does 1 mole of carbon dioxide weigh? So it's the same thing here. You're finding the molar mass. Okay, so I'm going to leave that for you guys to do as well. Let's see. Avogadro's law states that 1 mole of any gas occupies a volume of, that's the conversion factor for volume. Okay, guys. So that one, if we remember, is, let's see. Let's get this up. Where are you at? This one is 22.4 liters. Okay. That's how much a gas occupies in regards to its volume. It occupies a 22.4 liters in 1 mole of any gas. Okay. So in this problem, what volume do 2 moles of gas occupy at STP? So don't let this STP confuse you. It's just a certain temperature and pressure it has to be at in order for a gas to have the amount of volume of the 22.4. So STP just is part of the problem. So don't worry about that. You don't have to do anything with that. So let's set this problem up. So we have 2 moles. Okay, that's what's given. And we're going to multiply by the 22.4. So what are we looking for? We're looking for volume. So that means it's looking for liters. So if we have our conversion factor, 22.4 liters over 1 mole, if I'm looking for liters, geez. If I'm looking for these liters right here, that means I'm going to want this liters on top because that's what I'm looking for. That's what I'm looking for my result. So it'll be 22.4 liters over 1 mole of substance. Okay, so and also too, you can tell, remember, you can tell if you're doing it right if the moles cancel out. All right. And then we do the math and we get 44.8 liters. So in other words, we just multiply this by 2. Okay, guys, but because this is a chemistry class, we need to see your work. We need to see that you understand the process. Okay, that's the only thing that's of concern for me is that you understand the process. All right. So let's solve A, D, E, and G. Okay. So 13A, it's asking you how many moles of carbon atoms, okay, so that's your key word, atoms, are in 5.2 times 10 to the 25th power of atoms. Okay, so what I'm going to start with doing is I'm going to write down what is given. All right, let's make this a little bit bigger. There you go. All right, so let's write down what's given. So how many moles of, what's given is 5.2 times 10 to the 25th atoms. Okay, that's what's given to us in this problem. So let's put that over 1. Okay. Since we're dealing with atoms, what conversion factor can we use? What conversion factor refers to atoms? So you guys have this conversion, reference sheet. It has plenty of great resources. So if we go back to our reference sheet, look at this, perfect. Okay, so this guy right here to the right, this, stop highlighting it, sorry. There we go. So on this, what you guys want to do, okay, can I make it smaller? No, dang it. Sorry guys, there we go. So what we want to do with this, we want to, remember particles. Particles, we could also say that it is atoms. Whoa, I don't like that. Sorry guys, technical difficulties. Yeah. There we go. Make it small. Okay, so remember, particles describe atoms and they also describe molecules. Okay, so these two represent particles as well. Okay, so since the problem's asking for atoms, we want to use one of these two conversion factors. Okay, so we either want to use this one or we want to use this one. So let's look at where we're going. Are we going from moles to atoms, or are we going from atoms to moles? We'll go back to our problem. And we see that we're going from atoms to moles. So let's go back to our sheet here. Since we're going to atoms to moles, we're going to use this conversion factor. Okay, because we want to find moles, and moles is on top. Do you see this? Right? Moles is on top. So let's go back to our problem, and we're going to use the conversion factor 1 mole over 6.02 times 10 to the 23rd power of atoms. Okay, now what happens here? Boom, atoms cancel, and that's how we know that we're doing it right. Okay, so we plug this in our calculators. So remember, coefficients we divide. So we're going to take the 5.2 and divide it with the 6.02. And what happens to my powers? We subtract them. So what is 25 minus 23? We have to subtract the powers, and that gives us what? 2. So it'll turn into times 10. Whoops. Turn into times turn into times 10 to the second power, okay? Because it's, remember, 25 minus 23, okay? Excuse me. So if we type that in our calculators, we get 5.2 divided by 6.02. We should get 0.086. So let's do that again just to make sure. 5.2 divided by 6.02. Whoops. We get 0.8. That's what I thought. We get 0.8637. So I'm just going to round that to 0.86. Okay. So let's write that down. So we get 0.86 times 10 to the second power. But remember, this is improper. So we have to put it proper. Remember, has to be in between 1.0 and 9.99 in scientific notation. So then it could be 8.6 times 10 to the 1 power of moles of carbon. Okay, so this is our final answer. All right. Perfect. So on letter B, it is asking the same question, except we're going from moles to atoms. Okay. So we use the same process. We write down what's given, 4 moles over 1. Okay. We're going to multiply that by the conversion factor, 1 mole over 6.02 times 10 to the 23rd of atoms. Okay. And when we do the multiplication, same thing, 4 times 6.02, we get 24.08. Okay, so this turns into 24.08 times 10 to the 23. So this guy just goes along with the ride. Okay, the times 10 to the 23 just comes along with the ride because we only, remember, multiply the coefficients. Okay, so this turns into atoms. But remember, it's not proper, so we have to move it over one. So since we made this smaller, we have to add one over here. Okay, so it turns into 2.40 times, or we could put 2.41. So we could say 2.41 times 10 to the 24th atoms. All right. I'm very confident that C and D you guys could complete on your own. Letter F, go ahead and help you guys with this one real quick. Excuse me. So what is the number of moles in 250 liters of helium gas? So we start with 250 liters, okay, of helium. So we're going to go back to our reference sheet. We want to go from liters to moles. So what conversion factor are we going to use? We're going to use this guy, because we want to go from liters to moles. It's asking for moles, okay? So since we're looking for moles, we want moles to be on top. So 1 mole over the conversion factor, 22.4 liters, okay? Remember, this is over 1. And then what do we got to do here? Oh, look at liters cancel, right? This is helium. All right, so we just do the math. So we type in our calculators, 250 divided by 22.4 gives us 11.16. Come back over here. Video gives us 11.16 liters of helium gas. Okay. And that's it, guys. That is it. So the main thing is with doing these problems is setting up the conversion factor correctly. And I know that's the toughest part. But remember, whatever it's asking for, it's always going on the top. Okay. Or in this case, we have liters. We're going from liters to moles. So you could think of it as going from liters to moles. So we go back to our conversion factor and we're taking a look at our roadmap. So we're going from liters or volume to moles. We're going to use this conversion factor. All right. I will upload another real quick video to finish off the screencast for the last problem. Okay. So it should be a real quick, like 5-10 minute video. All right. Happy studying, guys.